A many-body wave function depends on the coordinates of all particles. Calculating it is a tough problem. For me, it's like climbing the north face of the Eiger mountain. And the worst thing is, once you have done it, you may not even feel comfortable up there. Remember, even when we are able to calculate a wave function, we might not be able to store it. So let us ask ourselves, why should we do it? What are we really heading for? For example, if I only want to have a view on a part of the valley, maybe I can take another route or even stop before getting to the top. So what do we want? Well, we want to describe and understand what we measure, what we observe. We want to calculate observables. In quantum mechanics, these are expectation values. Let us start from the expression in the grand canonical ensemble, which is a sum over states labeled alpha. The operator O stands for the measurement, and we have to integrate it with all many-body states psi alpha, which describe the system. Beta is proportional to the inverse temperature. E alpha is the energy of state alpha. Mu is the chemical potential. N alpha is the particle number in state alpha. And Z is the partition function, which is also a sum over states. For now, and for simplicity, let us stay at 0 temperature and fixed particle number n. Again, we have the operator that stands for the measurement, and we have the n-body ground state many-body wave function, which contains the information about the system we are looking at. So, once we fix the operator, we can say that the value of the observable is a functional of the many-body wave function. A functional is like a prescription. To a function, it associates a number. We know how to write this functional. It is this integral. So we know in principle what to do. But we still have the problem that in general, we cannot calculate the wave function, and we cannot store it, so we cannot calculate the integral. However, an integral always expresses something like an average. And when you do an average, you lose details. Let us look at an example. Suppose you calculate this integral of a simple function, and now you add an oscillation to the function. With symmetric boundaries of the integral, you cannot detect the oscillation in the result. So not all details of the integrand are important for the integral. This opens quite a few possibilities. 1. We may try to get rid of the details in the wave functions that are not important for certain observables, which means we may work with approximate wave functions. Some methods do this. For example, Hartree-Fock, configuration interaction, or quantum Monte Carlo. This is like modifying the mountain such that it will be easier to get to the top. If we do a good job, the final view from the mountain is unchanged, which is what we want. But that is usually difficult to achieve. A more radical idea is to ask, do we have at all to work with wave functions? Or could we rewrite this expression completely in terms of something else? Do we really have to climb the north face up to the top? In other words, can we access the essential information in a different way? Well, our observable is of course determined by the operator of the observable and by the Hamiltonian of the system. So for a given observable, at most, the result can depend on the form of the kinetic energy operator, the interaction, and the external potential. We consider that the kinetic energy operator and the Coulomb interaction are given. So the external potential contains sufficient information to determine the value of an observable. We can consider the expectation value O to be a functional of the external potential instead of a functional of the many-body wave function. Now let us pause and think. What is good? The 3n variables of the many-body wave function have disappeared in this way of looking at it. But what is this functional of the external potential? This is easier to see if we go back to the grand canonical ensemble. The sum over states is actually a trace. And since a trace is invariant, we can express our expectation value in this general form with the trace, and similarly for the partition function. Now, the system dependence is expressed by the Hamiltonian. And again, if the kinetic energy expression and the interaction are given, the result explicitly depends only on the external potential. So we have O as the functional of the external potential. But wait, how can we ever calculate this? This is super complicated. In the trace, we have huge integrals. We have to sum them all, and there are very many. Note that the operators do in general not commute, and we have still not used the fact that details may be integrated out. So that looks rather bad. What did we do? We moved from a known and simple expression with an ingredient that is too complex to be calculated to a complicated expression of a simpler ingredient. Did we gain anything? I do not know what you think. But be aware of one important thing. We almost never ever hope to solve a many-body problem exactly. What we want is an exact formula to start with. That's important. And then we will try to find good approximations. So here we really have a new strategy. We write expectation values as very complex functionals of a simple function. And we hope that we can find simple approximations to these functionals just because we expect that many details drop out or are not important due to the integrals and sums. And because it is a general strategy, this opens a whole range of possibilities. Indeed, could we maybe write our expectation values as functional of still another simple quantity? And would that be useful? Well, from the title of this course, you probably already know one possible answer.